All right, good afternoon. Let's start lecture. Okay. So the midterm is almost done. I only have one question. I marked only one question left, and there's half the class left. So there's a couple of days, and I should be able to finish. And then I'll ask T to upload the grades to Connect. Okay. And then we'll give you back the midterm, okay? Yeah. But judging from the marking up to now, honestly, it's not that great. Yeah. So really angry pounding there. But there are two questions that are practically just taking out. There was one question, same as assignments. The other question is a simplified version of assignment number 3. That's the third question, the fourth question. And the second question, more or less like the kind of quiz, not a quiz, the exercise we did in the lecture, right? So for some of you who didn't do well, just heads up, okay? And I might write a note asking you to come and see me, but it will be a wake-up call, I guess. Yeah. So anyway, let's continue on the lecture at here. Okay. Yeah. But I also wanted to see the difference. You know, somehow the difference this year, your attendance is very low. Maybe the room is too big. I don't know, but I feel like this year is lacking a little bit enthusiasm. So we need to keep up with it here. I know you're all busy, right? But coming to the class, I mean, this is, those who didn't come to class can't hear it, right? So coming to the class is important, yes?
I think the biggest problem was that there were 4 midterms that week and we were the last one. So that we had 3 midterms in the 2 days before, so we only had one night to study. So it might be better to do it after the reading week, since there's only one midterm in this class next year. Or spread out the midterms a bit more.
Yeah. The schedule, we had one coordinator actually trying to coordinate all the midterms. One of the midterm, not mine, jumped up. We used to be spread it out, but one of the midterms kind of squeezed in. So anyway, we're really trying to actually spread things out. Yeah. So, message heard. Yeah. Are we going to do that for the rest of the lecture? Okay. So you have a handout at here, and I want you to write the same time as me, okay? In terms of the Okay, so in the previous lecture, I think we covered this one or not. So basically, when we describe a gear, okay, we have a whole bunch of terminologies that are used relevant to the gear. Okay, so the most common one you will see is so-called the pitch circle. So pitch circle essentially, instead of drawing the whole detail of the gear, you probably will just draw 2 circles tangent to each other. And then that 2 circles are essentially the so-called pitch circle. Okay, many calculations are basically calculated based on the pitch circle at here. Okay, and we have a number of T's for the pinion, number of T's for the gear. Okay, and then there's also this so-called center-to-center distance, which is of course the addition of the diameter divided by 2. Okay, so you get basically the so-called center-to-center distance. Okay. Now coming back to this bigger one and here. Okay. So you have a handout, and I think last lecture I give you one of this. If you don't have, this is a little bigger space to write. If you want one, you can come here and pick up one. Okay. Otherwise, there's also handouts in today's handout there. Okay. Okay, so what are the important parameters here? Okay, there are 3 important circles, actually 4 or 5, but here it is 4 here. The circle, the most outside the circle at here, okay, this is called addendum circle. So I want you to get used to all of these terminologies at here, okay? The middle circle at here is called the pitch circle. And then the circle at the bottom in here, so this bottom circle here is called the dedendum circle. So these 3 circles are the most important circles. There's another circle called the base circle, which we will illustrate that in the next diagram. Okay. There's another circle here. This circle here is called the clearance circle. So this circle here is called the clearance circle. Okay. So clearance circle, basically, it's a circle that is tangent to the addendum circle of the meeting gear. So let's say if you have another gear, right, on the other end here. So that gear, let's say over like this. So this is basically the addendum circle for the other gear, right? So that addendum circle for the other gear will be tangent to this clearance circle at here. So give you a clearance between the dedendum of this circle and then the addendum for the other circle, or the other gear. Okay, yeah. So that's the clearance circle here. Along the pitch circle, okay, along this pitch circle here. So from one end of the tooth to the other end of the tooth at here. So this portion, this is called the tooth thickness. Okay, and from one end of the one point on this tooth to adjacent points, okay, on the adjacent tooth here, this will be called the width of space. So that's called the width of space. And if you add the tooth of thickness and the width of space together, so basically you get the distance from this end to here, okay, along the pitch circle. So from here to here along pitch circle. Then you get the so-called circular pitch. So over here, this is called circular pitch. Okay, so from here to here. Good? Yeah. Okay. And of course, there's another one here. So if you measure the thickness of this gear, so this is called face width. Okay, the face width. Face width, we typically use F, okay, to represent the face width. So this is sometimes a little bit misleading, because sometimes we see F is a force, right? But in this section here, somehow the F at here is the symbol used for the face width. Okay, yeah. In some literature, they use a small b for face width. Okay, yeah. Okay. Then over here, this portion in here, so there are a number of parameters that's important. Basically, if you look at the distance, the shorter distance between the addendum circle and the pitch circle at here, so this is basically called addendum. Okay, and we use small a to represent this addendum at here. So small a representing addendum. So typically for four teeth, four sides of teeth, this a at here, so this a equal to 1 over capital P. So, and I'll explain what the capital P is. Okay, maybe I'll just write it down now. Okay. So capital P at here, okay, is called diametral pitch. Okay, it's called diametral pitch. So what is diametral pitch basically? Okay, and diametral pitch is defined as P equal to N divided by D. Okay, N divided by D. N is the number of teeth, and D is the diameter of the gear. So N is number of teeth, and the small d is the diameter, okay, of okay, so N is number of teeth, and the D is the diameter of the pitch circle at here. Okay, so sometimes we call it pitch diameter basically. So you can see the unit for the diametric pitch is basically the number of teeth per inch, right? So that's the diametric pitch. Now coming back to on the same topic here, diametric pitch. Let's look at that concept, the circular pitch again. Okay, the circular pitch. For circular pitch, we use small p, okay, to represent the circular pitch. So you see the circular pitch is basically this is the distance from here to here, right? This is the distance from here. Okay. If you put it into mathematics, so the circular pitch basically is pi d over n. Okay, so there's a number of teeth, and then if you look at basically the total the parameter of the circle, right, and divided by that, and then you get this circular pitch at here. Okay. So there's a relationship between this diametral pitch and the circular pitch. If you look at these two, one simple manipulation, you'll see capital P times small p equal to pi. Okay, equal to pi. So that's the connection between diametral pitch and circular pitch. Diametric pitch is a very important parameter. If you want to have a pair of gears to drive each other or to mate with each other, then the diametric pitch has to be identical for these two gears. Okay, so that's the idea here. Okay, yeah. So coming back to this addendum. So the addendum here is related to the diametric pitch, which is 1 over capital P. Okay. And if you further down at here, if you look at the distance between the pitch circle and the dedendum circle at here, so this is called the dedendum. And we use a B for the dedendum. And the B at here are typically for full size tooth, it's a 1.25 over capital P, okay, the dedendum. So if you look at further here, so there's also a distance between the addendum circle and the clearing circle here. So this part we call that working depth. Okay, we call it working depth. Okay, and there's also distance between addendum circle and the dedendum circle here. So this is called the hole depth. So let's call it H. Okay. And of course, there's a distance between the clearing circle and the dedendum circle here. So this one here, you call that clearance. Okay. Let's call it clearance. Let's say C. Okay. C value. Okay. The C value at here are typically 0.25 over capital P. So that's your clearance value. Okay. So as you can see, your hole depth, basic H, is equal to A plus B plus C, right? A plus B plus C. And then the working depth, you can use this relationship. Working depth is A plus B, and then minus C, right? Okay. So that's from this figure. You know, a number of things that's important at here. Okay. Yes. A plus B? Which one? Oh yeah, yeah. The whole depth. Yeah, the whole depth is just A plus B. A plus B here. Yes. Thank you. Good. Working depth is A plus B minus C. So B minus C give you the distance between pitch circle and clearing circle, right? Yeah. Good. Okay. Going down a little bit to the other figure. Okay, so this figure here, there's a number of terminologies that we can illustrate on this figure. So this figure give you a whole bunch of circles again, but there are two solid circles. See, the two solid circles are tangent to each other. Okay, yeah. So these two, as we learned, these two circles, they are what circle? Pitch circle. Good. Okay, yeah. There's one circle that's not on the previous slides, which is the circle, okay, of this one here. So this circle, the inner circle, okay, the most inner circle, and also this circle here. Okay, there are two circles that are not on the previous slide. So these two circles, which arrow does that pointing to again? Here, yeah, these two arrows, right? These two arrows pointing to that two circles. So this is a so-called base circle. Okay, base circle. What is a base circle? So we'll actually look at a base circle a little bit very shortly. So base circle is a circle based on which the profile of the gear start to generate it. So you see the gear profile, right? Which is certain type of a curve, and that curve is generated based on this base circle, and that's a profile we call the involute profile, which I'll cover that shortly. But that's basically what base circle means. Okay. Yes.
What's the difference between base circle and the addendum?
Oh, sorry. My eyesight is actually, this is not a base circle. What am I talking about here? This is addendum circle, right? This one here, the bottom here is addendum circle. Base circle is this one. Sorry. Base circle is this circle here, the one that's above the dedendum circle. Which arrow is that? This arrow here, right? Yeah. So this is the base circle. Otherwise, there won't be any difference now, right? Yeah. Yeah, the one I just wrote it down here is dedendum circle. Okay. Yeah. So this is the base circle here. Okay. There's a portion of gear tooth profile generated from this point, which is the involute, and I'll teach that shortly. And there's a little portion of a tooth profile between the base circle and the dedendum circle, and that portion is actually a straight line. Then you chamfer that, and you fill it, right? And you see a little bit to fill it here. Okay, yeah. So this base circle is not on the previous one. Now there's a difference. You might don't confuse the base circle with the clearing circle, though. Okay, yeah. Remember, the clearing circle is what? It's the circle that actually tangent to the dedendum, to the addendum of the mating gear, right? Yeah. So if you look at the clearing circle, this is a clearing circle. If you have a gear of pinion on the other end, then there is a dedendum circle here. So that clearing circle is tangent to the dedendum circle. Okay. Yeah. And the base circle is a circle upon which the gear profile is generated. Good? Yeah. So of course you have an addendum, which is this portion here, so that's your addendum circle. Okay. So that covers all of this here, right? Yes.
So it's just coincidence that our base circle is at the same point, at the same place that our current circle would be?
This one, yeah, I don't think it's a coincidence. Yes, sort of a tangent to the addendum circle, right? Addendum circle.
But
yes.
It
Doesn't have to be. Yeah. So base circle. I'll show you a little bit animation later, just to show you some of the shortly. Okay? I'll show you something. Yeah. Okay, and then there is a horizontal line here that is basically tangent to both of the two page circles. We call the AB lines that are here. Okay, so this is called common tangent line. Okay, common tangent line. Above the common tangent line here, there is another angle between the common tangent line and then the line CD. Okay, this is CD at here. So the CD at here, if you look at the CD, right? The CD line, it's a line that is tangent to which two circles? To this circle and this circle, which we just said it's a base circles, right? Yeah. So the CD line is tangent to both of the base circle, and this CD line is called line of action. Okay, so line of action. Basically, this CD line is the perpendicular. If you look at this CD line, it's perpendicular to both of these tooth profile that is in contact at here. Because you're using one tooth to push the other, right? So the action-reaction force, because of this pushing, is along this line of action at here. Okay, that's what the line of action is. And the line of action intersect with this O1, O2, and this point at here is called the pitch point. So this capital P here is called the pitch point. Okay. So as I'm gonna cover very shortly, for the gear, there's only one line of action, which is this one. Okay. And that type of structure guarantees that you're going to have a constant angular velocity ratio, okay, because of this kind of a tooth profile and a structure of the curve. Okay, yeah. The angle between the line of action and a common line here, so we call that phi. So this is called pressure angle. So pressure angle essentially is how the force is being pressed, right, from one tooth to the other tooth. So the pressure angle is a very important angle. In gearing, normally 20-25 degrees. Okay, yeah, and we use 20 degrees quite a lot. There are also sometimes 14.5 degrees. Okay, you can literally use actually any angles for the pressure angle, but these are the three pressure angles that the industry has been used for the gears that you buy, essentially. Okay, you specify pressure angle by specifying one of these values. Okay. So if you actually visualize this, if you visualize, you have two drums, right? You have two drums, and then the pressure, the line of action, is like a string that is tangent to the two drums or the two cylinders at here. So that tangent, very tightly tangent here. So then these two basically will move, right? Will be moving and constrained by this line from here to here, right? Okay. So this line here, they're not gonna relax. They'll always be like a very tightly stretched between these two cylinders, basically. Okay, yeah. So that's pressure angle. And now, if you look at the radius from the origin of the pinion to the base circle at here, so we call that let's say RBP. Okay, so that's basically radius of the base circle. Okay, radius base circle. And then from this O1 up to this pitch point, so we can call that RP. So that's the pitch circle radius. Right, that's the pitch circle radius. Okay. And that's the same radius from here to there, so this is also the RP at here. Okay. So this is the pinning, P at here representing pinning. Okay, representing pinning at here. And then very simple geometry, you will see that the angle between this RBP and RG, this is a pressure angle. because this is perpendicular here. Okay, so this is a tangent point. If you connect O1 with the tangent point, and then you get the pressure angle, which is the phi at here. Okay. Yeah. Similarly, for the gear part, you get this is RG, and this is your RBG. So the base circle radius for the gear, and this is the pitch radius for the gear. Okay, and here's your pressure angle. Okay. So if you look at this right triangle, so if you have a right triangle here, this is the right triangle, right? This is right triangle here. Then you can establish a connection between the base circle radius and the pitch circle radius, which is what? So your RBP equal to RP times cosine phi, or similarly RBG equal to RG times cosine phi. Okay. So that's the connection between pressure angle, pitch circle radius, and the base circle radius. Good? Yeah. So pitch circle essentially is a cylinder, you know, it's there. So if you think about it, right? If I choose a different pressure angle here, if I choose a different pressure angle, 14.5, 20, or 25, plug in here. If this is not going to change, if RP is not going to change. If I choose a different pressure angle, what is the effect on the base circle radius? Right, you can see that. So if it's the phi going up from 14.5 to 25, if this is going up, this is not changed, then this number will actually go up or go down. Go down, right? Go down. So for higher pressure angle, you end up with a smaller base circle radius, right? Yeah. And then later I'll show you the picture. What's the effect of that on in terms of the generation, the involute profile? Okay. So those are the terminologies essentially that you probably will come across quite often in the assignments or in the near future for gear designs here. Okay. Yeah. Another thing that we want to touch upon is the gear tooth profile. Okay. Before we talk about the gear tooth profile, let's talk about a little bit the very general case set here. So let's say, suppose that you use one object pushing the other objects, and with both of the objects are fixed on this at a certain pivotal points at here. Okay. Yeah. Now, if your objective is to generate a constant angular velocity ratio, okay, so if your objective is a constant, okay, if the objective is maintain constant angular velocity ratio, okay. Objective is, that's very common, right? You probably learned in kinematics and the machine mechanism, the 381. There's a very interesting mechanical component, which is called the cam, right? So the cam, essentially the surface of the cam, okay, maintains this kind of surface, which will give you the objective maintaining a constant angular velocity ratio. And this type of if you can achieve this objective using this sort of a surface set here, this is give you the so-called conjugate action. Okay, this so-called will give you the so-called conjugate action. Okay, so the two surfaces, if they can generate the conjugate action, basically they have this constant angular velocity ratio. Now, if this happens, then there is this action-reaction line here, or the line of action, like the one I showed you for the gear. Then that line of action will pass through this pitch point P. Okay, will definitely pass through pitch point P. However, the difference is for this one here, if you move it to the next location, then you might have a different line of action. You might have a line of action that's this, but the line of action will still go through this pitch point P. Okay, so basically this way you will be able to maintain this constant angular velocity ratio at here. Okay, yeah. So that type of profile is something actually when you design a gear, that's basically what you want. You want to maintain a constant angular velocity ratio, right? So you want to have a conjugate action at here. So what type of surface profile will give you that this objective then, right? So this is basically the profile for the gear. Okay, yeah. So profile of the gear is a so-called involute profile. Okay, involute profile. So what is the involute then, right? The involute profile for gear. Imagine this: you have a, let's say, a cylinder, okay, and you have a string wrapped around this cylinder, okay, very tightly. So now what you start to do is you start to unwrap this string from this cylinder. Okay, so you grab one end of the string. Okay, so this is the one end of the string at here. When you unwrap this string from the cylinder, make sure the string is stretched tightly every moment, and then you basically unwrap that string, right, from the cylinder. Is that good? Now if you trace out the tape trajectory of the string, which is this one here, and give you this so-called involute curve. The gear profile is basically part of the involute curve from here, let's say from here to here. And this circle is the circle I just mentioned. That's the base circle. Okay? Yeah. So that the gear profile, this portion in here, is this involute profile. And it's generated in a manner like this, basically. Is that good? Yeah, that's what involute profile. You can mathematically model this involute profile. This is a parametric equation. You can mathematically model this. You can take a look at my lecture notes, which provide more detailed derivation of what's the mathematical expression for the involute profile. Okay, so let's say, suppose that I'm gonna generate the parametric equation or involute profile starting from this A location. Okay, starting from the A location, and then basically the red line is how the trajectory, the tape of the piece of the wire, if you are a string, if you start to unwrap or unwind from this cylinder right here. Okay, yeah. So if you look at the lecture notes, if you derive this the parametric equation, you'll see that for this piece of curve, involute curve here, so x will equal to r times cosine t plus rt sine t, and y equal to r times sine t minus rt cosine t. So you'll get a parametric equation describing this involute profile here. Okay? Yeah. So in this week's tutorial, I sent you guys an email, the exercise to use SolidWorks to generate the gear. By basically going through the exercise, you get familiar with all the different terminologies. And one of the approaches to generate this gear profile using parametric equation. Okay, so you can literally generate the parametric equation, not necessarily starting at the A location. You can generate at any other location. Okay, at any other location by changing the t value. For example, if you're going to generate starting point is this B location, all you need to do is you change the t to t plus 90 degree. Okay, so then that curve, instead of starting from A location, it'll start from the B location. Okay, yeah. So for example, if you even like this, if you wanted to generate envelope profile, instead of going this way, basically you unwrap that clockwise instead of counterclockwise. So the green one in here. So all you need to do is you just need to change the t to negative t. Okay. Then that parametric equation will be able to generate a curve in a different direction, basically. Okay. So bring your computer to the tutorial. Okay. And hopefully within the 1 hour you will be able to finish actually drawing a gear. Okay, it's an equation-driven gear basically. Okay. Okay, so that's envelope profile for the gear. Okay, and over here, let's see in the terminology at here. We have a concept called pressure angle and also line of action in here. Okay, so just to quickly touch upon again about this pressure angle. Okay, yeah. So let me show you an small animation in here. Okay. This is a very useful application, but unfortunately it's not free. So I use it for illustration. So this one here essentially demonstrating the meshing of two gears at here. So I'm gonna show you. You can literally see the action reaction in here. Okay, yeah. So you can see this is the line from the origin of the circle to this circle here. So as we just learned, what do you think this circle is? That's right. This is the base circle here. So you connect these two tangent points for the two base circle, and that's the line of action at here. Okay, line of action. And then I want you to watch carefully in terms of as you move the gear, in terms of the contact points between the two teeth, okay, between the pinion teeth and the gear teeth. If you just watch this contact point at here. So what you see is, see the contact points between the two teeth. They are always on which line? They're always on that line of action here, right? You're always on the line of action, okay? Yeah. And that's basically what we call the pressure angle, right? It's the force is always in that direction. That's the unique thing about the envelope profile. Remember that the conjugate action I mentioned, the line of action not necessarily has to be unique all the time, but for gears envelope profile, and the line of action is always unique, it's always this direction with the pressure angle, right? With the given pressure angle. Okay, yeah. So, and if you look at the contact point between other pairs of gears, you'll see the basically similar phenomena. So they're all on the same line of actions at here. Okay, the same line of actions. Okay. So that's pressure angle, okay? That's pressure angle. Okay. Okay, one more concept, contact ratio. Okay. Now, contact ratio is a basically, let me write down it here. So you have your handout, you can write something there. So if this is a measure It's a measure of the average number of pairs of the teeth that are in contact. Okay, yeah. So when you use a gear, a pinion drives a gear, okay, and by transmitting certain power from one end to the other end. And of course, you have the force basically being transmitted, right, by when the pinion's teeth is pressing the gear's teeth. Okay, so what you really want is you don't want just all the time just one pair of teeth in contact, right? What you want is you want a certain type of a load sharing. So which basically means you want probably more than just one pair of gear teeth in contact with each other. So that's what the contact ratio basically wanted to tell us at here. What's basically the measure of the average number of pair of teeth that are in contact. We typically use MC to represent this concept at here. Okay, this concept. So before we label down all the terminologies that are here, okay, and there's one thing I want you to also observe is there's one statement. The tooth contact begins and ends at the intersections of the two addendum circles with a pressure line. So what does that mean basically is where is basically the extreme points between the contacts of the gear teeth. Okay? Yeah. So let's look at this animation right here. Okay? Let's find a good starting point. Okay, right here. So look at this this point here. Okay, look at this point here. Now if I move it a little bit, okay, move it let's say to this side here, a little bit to this side here. So then what happens is you see this blue dotted here, okay, this dotted here. Oh, that's so annoying. Okay, so if I move slightly away from here, you see, I should probably push it. Let's imagine it's the red one driving this blue one in here. Okay. So if I go away from here, they're not actually in contact right at this location. That's when this red teeth started to engage with this blue teeth, and then started basically to drive it, okay, to the direction, right, giving like this. Is that okay? So if you watch this location in here, what's the location? This is a location intersecting between this circle, which is, what do we call this circle again? Addendum circle, and which line? The reaction line. So this dotted here is basically one of the extreme points defining the contact point. Okay, and then if you go to the other side, the other side is basically the addendum circle for the other gear intersecting with the line of reaction, and that is the exit point. So let's move it. Start moving again. Okay, watch for this contact point. So it's still in contact, right? So we keep going, that little location there. Okay, right after that. And that's where they started to disengage, basically. Okay? Yeah. So, and this is the distance I showed it over here from A to B. Okay? And that's the distance. We call that action line. The distance, that's what we call, this is called the length of action in here. Okay, this is called the length action from A to B. Okay, yeah. Now within the circle here, you see there's a called arc approach QA and arc of recess QR. Okay, so in total, if you add this QA and a QR, in total we call that the QT. So QT is called arc of action. So this is called the length of action, right? And then this total arc length is called arc of action at here. Okay, so arc of action. Yeah. So if we use small p, as we denote small p as a circular pitch on page circle. Okay, and we use a small pb, and we'll call that circular pitch on base circle. Okay, so along this circle here, right, you have this parameter called circular pitch. That's circular pitch on page circle. And then you also on the base circle, you also have basically similar circular pitch, but they're different values. Okay, they're different values. Now these two are connected with this formula here. Small pb equal to small p times cosine pressure angle. Okay, pressure angle. Yeah. Now, in terms of the value for the length of action, here's a formula. Okay, here's a formula for calculating the length of action here. Each one of the symbols are denoted below it here. For example, RPA is the radius of pinion's addendum circle, and RBP is the base circle for the pinion, right, like this. And C is the center to center distance. The derivation of this formula is given in my lecture notes. Okay, so you can take a look at that for the details of the derivation at here. Okay, yeah. So now the contact ratio MC. Okay, you can calculate the contact ratio MC using these two formulas, using either the ratio between LAB and PB, or you can use the arc of action divided by the circular pitch. So either these two will give you the same value, which is the contact ratio. Okay, in terms of the proof, why this equal to this, and also have the proof in my lecture notes. Okay, if you're interested, you can take a look at that. It's purely geometry, basically. Okay, purely geometry. The MC value are typically recommended to be greater than 1.2. So if you have a very small MC, then it might not be a good pair of gears. Okay. Any questions? Okay? Yeah. So let's continue it here. Interference. Okay? This is another concept related to the gear. Okay? So what's interference first of all? Okay? Yeah. Before we talk about interference, I think we should probably just jog your mind in terms of the gear profile here. Okay, gear profile. So this is typically how you draw a gear. You know, you can start with the base circle. Okay, so let's see, this is the base circle here. So starting from the base circle, and then you will be able to generate that involute profile, right? Using parametric equation. Okay, yeah. And you also have so you could also have, of course, the important one, which is the pitch circle, right? The pitch circle here, and then of course finally the outer side circle, which is addendum circle. Okay, addendum circle. So those circles, as long as you have, let's say, the number of t's, diametral pitch, okay, so these circles will actually determine the important parameters. So if you have a diametral pitch, a number of t's, then you can determine the pitch circle radius, right? Yeah. Okay. So at the bottom here, you also have another one here. This is the dedendum circle, right? Okay, this is dedendum circle. So the question here is, if this is the origin, okay, this is the origin for all of the circles here. So the question is basically, you see, what is the gear profile between the base circle and the dedendum circle? Right? What would be the profile between the base circle and the dedendum circle? Between the base circle and the addendum, this is an involute profile. That's fine, right? That's what we want. That's the gear's profile. So between the base circle and dedendum circle, and the profile, what you typically do is, it's a straight line. So you connect these two here, this portion. Okay, there's a straight lines here. That's the profile between base circle and the dedendum circle. It is not involute profile. Okay. So now here comes the question now. You have a gear, let's say for example, gear tooth like this type of profile, and then you have another gear tooth, okay, which is the mating gear, for example. Okay, yeah. There is a possibility that the other gear tooth will get in contact with this non-involute portion of the gear profile. Okay, so there's a probability like that. And if that happens, that's what is called interference. Okay, yeah, that's what it's called interference. So essentially, you want it to be always the contact points between the two teeth are always within this involute portion, not between the involute and the straight line, basically. Okay, yeah. So if you go to a dentist and they give you a filling, what's the last step they do? Right? They fill your teeth, and then the last step, I don't know the technical term, okay, but you know, they have a piece of a blue paper, that kind of thing, right? And they want you to tap on it, and they see a color, and then they grind it a little bit more, until they don't see the color, isn't it, right? If they don't do that, what happens? When you bite on each other, what happens? They don't mesh properly, and you actually will feel a sense of what? Something always digging into the others, right? Yeah. That's basically what the interference will happen right here. Yes?
So that would basically happen if the opposite addendum line crosses the baseline, right?
Opposite of addendum line cross. Right. So what you're saying is like this case I'm drawing at here, right?
Yeah.
So basically my dedendum is at below the base circle, right? So if it's below, then I will have a portion of a straight line at here, right?
Yeah.
Yeah. Now that basically will give the opportunity or the chance for the interference to happen.
Yeah.
Yes.
What I'm saying is that the addendum line from the other gear.
Oh, yeah.
Gear.
Yeah.
If that addendum line is below the baseline, then there will be interference, right?
Right. Yeah. Yes. Yeah. So, like the drawing showing it here, right? So I'll show you some little bit animation in it here as to show you what the case of interference basically. Okay. Yeah. Interference happens when you have a sort of a combination of teeth numbers, okay, and also pressure angles at metric page. Okay. So let's say I'm going to lower my pinion number. Okay, lower my pinion number to maybe 9. Okay. So maybe 9 here. So now you see, this is the red one is the pinion. Okay. Right now the number of teeth for the pinion is 9. Okay. Yeah. So what you see at here, okay, from this animation here, okay, you see there's a certain portion of material are being carved out, right? Being basically removed. Okay. Now, if you don't remove this portion, just imagine, right? Just imagine you have a straight line goes from this point right to this origin at the bottom here. Okay. There's a straight line portion from here to the end. So then what happens? You see that if I move around, you'll see some of the. If I look at this contact point here, if you draw a line goes down to here, so you can clearly see that this portion of the involute will what? Will dig into that straight line portion, right? Yeah, that's basically interference. And what this drawing at here, what it does is, it do a process, manufacturing process called undercut, because with this number of teeth, 9, there will be interference. But if your customer insists, I want to use 9, then what do? Then you have to carve out, remove a certain portion of the material from here. Okay, that's called undercut to prevent this interference from happening, basically. Okay, yeah. And if you're interested, actually there's some inherent geometric relationship at here. Now, if you look at the current situation, right? Here is the tangent point between the line of action and the base circle. This is the location of the tangent point, and this is basically the vertical line here, right? Perpendicular tangent line. And these two blue dots, they're the what? The line of action, the two extreme points, right? The two extreme points. And currently, one of the blue dots is actually outside this tangent point. And that actually is one of the constraints. If you don't want interference, both of the blue dots needs to be within these tangent points. Watch what happens if I increase this number of teeth pinion, okay? And also watch this blue dots that are here. If I increase this, you see that blue dots? Where did it go? Now it moves into what? Moves into these two tangent points. Okay? Yeah. So mathematically, you can actually use this constraint, which is one of the formulas I'll give it to you, to derive what would be the minimum number of teeth to avoid interference. Right? So that's a constraint you can use to avoid interference at here. Okay? So we still have some time. So this is basically the couple of formulas I want to write down at here. Okay. So what will be the number of teeth to prevent interference? So to prevent interference, what is the minimum number of teeth, okay, for the pinion NP? If gear ratio we use M for gear ratio, and NG over NP, we call NG over NP is a gear ratio. If that number is greater than 1, okay, then the smallest number of teeth on pinning is the following formula. Okay. So you use this formula to calculate the smallest number of pinning teeth if the gear ratio is more than 1, in order to avoid interference. Okay, in order to avoid interference. Not only the requirement on the smallest number of, or the minimum number of pinning teeth, there's also a requirement on the largest number of teeth for gear. Okay, there's also the largest number of teeth for gear. And this formula is given for the NG, which is NP square sine phi square minus 4k square, and 4k minus 2NP sine phi square. So these two formulas comes in a pair. Okay, they come in a pair, and then you use it as a comparison. So I'll show you a figure, a table based on this calculation here. So let's see how do we calculate this. Okay, there's one parameter in the two formulas, the key parameter. Okay, the key will equal to 1 for full tooth. Okay, and typically it's a full tooth. But there's, for the gear, there's another type of tooth called a stub tooth. So it's a little short. Okay, short in terms of height. If that's the case, then you use 0.8, okay, for stub tooth. And M is the gear ratio, phi is the pressure angle. You plug in all the numbers, you'll be able to get the NP and NG. So let's say, give you an example here. So let's say we take pressure angle 20 degree and as a calculation. Okay. Now if you plug in phi equal to 20 degree, okay, and if we, let's say we choose, if we say, okay, I'm going to choose a number of teeth for the pinning in 13, then we plug in into the this second formula here. We're going to get NG will equal to 16. Okay. Yeah. So that basically what it's saying is, if your pinning number is 13, then in order to avoid interference, the maximum number of teeth on the gear is 16. Okay?
Oh,
yes?
K is not 1 for when you have a cutoff?
K is 1 when you have a full size tooth.
And
this is a 0.8 when you have a so-called stub tooth. It's a shorter type of a tooth. Yeah. Okay? So if you try a few numbers, let's say if this is 16, and then you get NG is 101, so it increases significantly. Now, when your pinning teeth is 18, then your maximum NG will become infinite, basically. So what does that mean? Is basically if you have a 18 on the pinning, then you can choose any number of gear teeth. Okay? Yeah. Of course, minimum is 18, right? You want to maintain that ratio to be greater than 1. Okay. So if you look at this, for example, if you look at this one here, right, then you get the maximum ratio is what? Is 101 over 16, right? That's maximum gear ratio you could get. Okay. Yeah. Yes.
This is for when there's no cutoff, right? When there's no undercut, I mean.
Right. Right. Yes.
Or
Yeah.
no undercut.
That's right. No undercut. No interference. No undercut. Yes. So if there is interference, and then you can use undercut to avoid it, right? Yeah. So this figure right here, shows you when 20 degree you have this combination. If you have a 25 degree, then you have this combination right here. Okay. So it clearly says, you see, as pressure angle is increasing, then the requirement on the smallest number of pinion teeth, right? You see here, this is 12, this is 18, this is 32. Okay, it's getting smaller, right? And that the following figure here shows you the difference between or the effect from the pressure angle. As pressure angle going up, one of the formula I just showed you, the base circle radius will become smaller. So you see the base circle radius will become smaller. So which basically means you have more involute profile at here, right? Yeah, when you have a higher pressure angle. Okay, so more involute profiles, and then there's less chance of basically interference. Okay, yeah, that's the concept of interference. Okay. In the future projects, the first step, okay, that you do is actually to calculate what is the minimum number of the teeth on the pinion in order to have no interference. So based on the given specifications, like a gear ratio will be given 3.5, if I remember correctly. Then calculate the minimum number of pinion teeth, okay, to avoid interference, and you will use this formula, right, to calculate the minimum number of teeth for the pinion to avoid interference. Okay. Then from there, you can come up with different combinations of pinion and gear teeth, satisfy the gear ratio and also satisfy other requirements. Okay. Yeah. Okay. So one more concept, gear ratio, and also something to do with gear train in here. Okay. You don't just use one pair of gear. Okay. You often have a number of gears connected together, to form a so-called gear train. Okay. But first of all, let's understand the concept of gear ratio again. Okay. So if you have two gears, okay, connected, meshed with each other, okay, so then chances are, okay, it has a connection of so let's say if this is input, for example, this is output at here. So omega 1 is the input angular velocity, omega 2 is the output angular velocity at here. Okay. You may have, let's see, N1, N2 for the number of teeth for this gear and for that gear. And we use R1 and R2 for the two radius at here. So one way defining the gear ratio is any one of the combination here will be fine. Okay. So any one of this expression, you use the output angular velocity divided by the input angular velocity, okay, and then equal to the number of teeth of the input minus divided by the number of teeth of the output, okay, or R1 over R2. They're all the same. Okay, this is basically your gear ratio at here. Okay, gear ratio. Yes.
You previously used M for gear ratio. It doesn't really matter.
Yeah, it doesn't matter. Yeah. But very good observation. You almost see. However, okay, just to emphasize it here, in actually in automotive industry, okay, the gear ratio. That's the one I used in the previous example. Okay, they can use just number of teeth on gear and divided by number of teeth on pinion. Okay, it's actually a reverse number from this expression. Okay, yeah. So if you have a gear tooth 30, then pinion tooth 15, then you got a gear ratio of 2. But if you cut into this one here, you actually got a 1 over 2. Okay, yeah. So really doesn't matter. Just bear in mind of the context for any questions or any things that you do. Okay, yeah. Now one more thing. Let's talk about the gear train property. Okay, so if it's not just two gears connected to each other, if there's actually a number of gears connected to each other. So here's one example I'll show you here. Okay. So let's say I have a small gear here and relatively bigger here, and then a small gear over here. Okay, but there's a bigger gear. Okay, like this. I'll explain a little bit here. Okay. And finally another gear here. Okay, so let's just suppose we have a gear train like this. So I'm going to call this number 2, this is number 3, this is number 4, okay, and this is number 5, and this is number 6, for example. Okay, yeah. So let's visualize how the motion is being generated. So number 2, let's say, moves with a n2 revolute per minute or velocity like this. So number 2 push number 3. So apparently number 3 will go this way now, right? So let's say number 2 has n2 number of teeth, and this has n3 number of teeth. Okay, and this 4 has n4 number of teeth. This one has n5 number of teeth, and this one has n6 number of teeth. Okay. So if 3 goes this way, so the 4 and the 5 at here. Okay. So 4 and a 5 here, basically you can visualize it as 2 gears attached to the same shaft. Okay, so 4 at here is being driven by 3. Okay, so which goes this way, and then 5 is attached to the same shaft as number 4. So this 5 will go this way, and the 6, of course, finally will go this way. So that's the motion sequencing, right? Because the gear train at here. Okay, yeah. Then for this type of problem, there's a very important concept called the train value. Okay, so the train value will give us the ratio between the angular velocities. So how train value is defined is basically so I write down the general formula, the train value here. Okay, so train value E is equal to positive, negative, a ratio. On the numerator, it's the product of driving tooth numbers. The bottom here is the product of the driven tooth numbers. Okay, so that's the formula for calculating train value E at here. So let's take a look at this example here. How's that related to this example? So for this particular example, the E, okay, equal to numerator is the product of the driving tooth number. So let's look at this sequence of gear here. Which one is the driving? Number 2 is the driving, right? Number 2 is the driving here, so that's N2. And number 3 is being driven. However, number 3 is also what? Driving. So number 3. So that's number 3 is actually called idle gear. Okay. And then number 4 is a driving one, but number 5 is a driving gear. So driving 6. So that's the numerator. And denominator is a driving one. So there's N3 still driven, and then N4 and N6. So that's the ratio, right? What about the positive and negative here? So the positive and negative will indicate the direction change. So if you look at the current one here, there's apparently the direction change. So you need a negative sign in the front. Okay. So that's the train value. Okay. So the usage of train value basically is, if you ask is, okay, so if I know the input angular velocity omega 1, then all we need to do is time E value, then you get the output angular velocity omega 6. Okay? Yeah. So that's gear train and gear ratio. Okay. Any questions? So good? I'll stop here, then we'll look at the force, particularly for spur gear and helical gear. And when I finish this, we'll get into the gear design. Okay. Mm-hmm.